All right, so we have, again, our differential equation with constant coefficients corresponding to this auxiliary equation. We've looked at the first two cases, okay, where we have distinct roots and repeated real roots. And now we're going to consider the case where we have complex conjugate roots, okay? In this case, of course, we have that b squared minus 4ac is negative, strictly less than 0. And we get two roots that are complex and complex conjugates of each other, right? So they have this form here where alpha is equal to negative b over 2a and beta is equal to the square root of the absolute value of b squared minus 4ac over 2a, okay? Because we already considered, beta already considers the negative in the square root. We have the I already factored out. And so that's why there's an absolute value there, okay? Otherwise, you'll get negative and then have another I, and that just defeats the purpose of how we defined alpha and beta here. Okay, so we then get, two distinct solutions, one corresponding to M1, and so here's one solution, and here's the second. And in some sense, we could just be done, okay? And in, advanced textbooks, you are done at this point. But our work is in the real numbers, so we'd rather avoid having complex solutions and working with the imaginary number, okay? And so we can actually avoid working with imaginary numbers altogether because we can add constant multiples of the solutions together and still get a solution, okay? So notice with Euler's formula, e to the I theta is equal to this, okay? It's just a fact, take it as a fact, Euler's formula. And what we're going to do is just take these two solutions, add them together, and multiply by a half. So we get this expression here. Pull out the e to the alpha x from each of these, okay? And then pull it out here from both terms there. And you're left with this expression in the parentheses. Now apply Euler's formula to that expression. You get this here. Cosine is an even function, so these will add. But sine is an odd function, and so sine of negative beta x is equal to negative sine beta x, and so these will subtract, and you end up with this expression here. And because this was a constant times, 1/2 y1 bar plus 1/2 y2 bar, or a sum of constant multiples of solutions we already found, we know that it's also a solution from the theorem that we looked at when we looked at the general theory of linear equations. Similarly, we could multiply the difference of these two solutions by negative I over 2, and we end up getting, if you just follow the similar steps and apply Euler's formula, you'll end up getting that this here is also a solution, okay? And this solution is linearly independent from this solution, so we found two real linearly independent solutions, and so those constitute our fundamental set for this second order equation. And we then have our general solution, which looks like this, okay? It's of this form here. Let's look at a concrete example, okay? Here we have this differential equation. We're actually going to apply it, we're going to apply initial conditions on this, okay? So we're going to turn it into an IVP problem just to see how that works here in the context of second order differential equations. So we have our auxiliary equation. We get two complex roots. And notice that they're always conjugates of each other. Okay, that's just because the auxiliary equation here has real coefficients. And so you're always going to get these as complex conjugates. Our beta is 2. Our alpha is negative 1/2. And so our general solution is going to follow this form here where alpha is -1/2 and beta is 2. And there goes our general solution. Now this is an IVP, initial value problem, so we do want to solve for these constants using our initial conditions. We know they're going to have a unique solution by our theory of linear equations we looked at. And so we have 1, the condition that -1 is equal to y0, and we just take 0 and plug it into our general solution here. Okay, so you always got to separate in your mind the left side, which is coming from the problem, it's a given, and this side where you're plugging in what y of 0 is into your general form. You do that, and you end up getting, this is going to be 0 here, and so you end up getting that C1 must equal -1. Okay, so we found what C1 is. We fixed that constant. Now we want to fix the second one. And so what you'll do is take the derivative of this general form, and of course you're going to have to use the product rule. And, if you do that and you use the product rule, you have this long expression there, and I just plug in 0 into it. Okay, otherwise it would be an x everywhere here. Where you see a 0, it's an x. That's what happens when you take the derivative of this expression. So you take the derivative, you plug in 0 after taking the derivative, and you set this equal to 2 because that's our initial condition there. And you end up with C2 is equal to 3/4, and so you end up with this unique solution to the IVP that we see here.